Example number 1 from Monday, November 20th. If you throw a ball directly up into the air with a velocity of 40 meters per second, when will the ball come back to your hand? I picked 40 meters per second because according to old Google, that is the average for a professional baseball pitcher. So let's see. A baseball pitcher throws a ball straight up into the air, initial velocity of 40 meters per second. We've actually solved a question like this in the past, where we said the initial was 40. We then made the safe assumption that the final is 0, because it would come to a stop before it starts making its way back down. We know the acceleration during this time would be negative 9.8 due to gravity. And we can do that, or use that, and some of our other simpler equations to figure out how long it takes to get to the top. And then we doubled it, because we could go and prove that it would take the same amount of time to start at 0 and then accelerate back up to 40, where he would catch it. But there's some assumptions in there that, while they are fair and true, we can solve this without making those assumptions. And using the new way, using the quadratic formula, will actually be notably faster. Because all we need to start with is our big ugly equation, our displacement equation for an object that has velocity. Initial velocity times time plus 1/2 the acceleration times t squared. We know the displacement. It's going to go up, it's going to come back down, we're going to catch it, so the displacement would be 0. The initial velocity, 40. And the acceleration, negative 9.8. Now in the past, we said this was an issue because we have a t and a t squared. That's effectively 2 unknown variables, 1 expression, so we couldn't solve for t. But that's where the quadratic formula comes in. Using that, we can solve for this. And just to make things clear, I'm going to reformat this a little bit so it's in the traditional ax squared plus bx plus c equal to 0 format. So our t squared here, that would be equivalent to our x squared. So I'm going to put the 1/2 negative 9.8 t squared on the far left plus 40t, because that t is equivalent to our x. And here we don't have a constant, or rather, we do have a constant. It would just be plus 0 is equal to, well, 0. Now, if this was set up a little bit differently and we weren't starting at an initial position of 0, we could call this our initial position, and this would be our final position, as we'll see when we get to some of those canon examples. But for now, we won't worry too much about that. So we have our a, which I'm actually going to simplify this a tiny bit. 1/2 times negative 9.8 would be negative 4.9. Rewrite the rest. And there we go. So negative 4.9, that's our a. 40, that's our b. 0, that's our c. So jumping over to the quadratic formula, x is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. Or in this case, negative 40 plus minus square root 40 squared minus 4. Our a is negative 4.9. Our c, though, is 0. So this whole second term, the 4ac bit, is just going to turn into 0. all of that will be over 2a. 2 times negative 4.9. Now I can simplify this quite a bit before I break it up and solve it once for the positive and once for the negative. X will be negative 40 plus minus. In this square root business, I can just toss that into a calculator and get a number out of it. Well, once again, I really only need to do the square root of 40 squared, since the whole right bit here all just goes away. And I suppose, calculator not really needed here, the square root of 40 squared would just be 40. All over 2a, 2 times 4.9, well, we're back to that negative 9.8. And here is where I would break it up, solve twice. Say negative 40 plus 40 divided by negative 9.8. And then negative 40 minus negative 40 minus 40 divided by negative 9.8. So at the top, I've got negative 40 plus 40. That would give me 0. 0 divided by anything is 0. And we're talking about time here, as just a reminder. Our x in this case, all of these x's here, here, and here should actually be written as delta t's because we're solving for time. But I'm going to get rid of that just to clean it up a bit. There we go. Back over here. So one of our potential answers is 0 seconds. Our other potential answer, what does this come out to be? Comes out to be 8.16 seconds. Just like in math, these aren't two potential answers. That was actually bad wording. These are the two answers. Our time, that's the time in which our object in question was at 0. In this physics case, when our object was at 0 meters. Well, we started at 0, so it makes sense that at time 0, we were at 0. That's great. But that's not what we're looking for. We know that already. That's where we started. The time we care about is this one down here. We throw it up, 8.16 seconds later, we catch the ball. Make sure we answer the question. When will the ball come back to your hand? There we go. We answered it. So that's example number 1. Let's move on to example number 2. Oh, look, example number 2 is almost the exact same question. The only thing that changed was the number. So the first time around, I went through, going every step of the way. This time, I'm going to move through it a little faster and try to give a good example of what you can do once you get used to the process. So you don't, once you're comfortable enough to where you don't need to do every single little step. But that being said, I would start by doing every single little step like we did last time. Well, let's try this one. Initial velocity, 24 meters per second. Throwing it straight up, so I could also call that initial velocity y. That's all I care about. Still no acceleration, would be negative 9.8, because assuming we're throwing this ball on Earth. And our initial position, we'll say our hand is 0. And we're looking for time. The time in which it will come back to 0. So we already know we've got big ugly equation. There it is in all its glory. We're going to switch things around just so it's a little bit more matching with the standard form. I'm going to add that plus 0, the C that we need. Really, again, since I'm putting a plus 0 here, that's my initial position. So this delta x, I really should write that as x final, since we're interested in knowing when our final will get back to 0. Oftentimes, we can interchange final position with delta x, but only if we started at 0. So let's plug in some numbers. 1/2, negative 9.8. Initial velocity, 24. I like to simplify that 1/2, negative 9.8 a bit, just because I try to get rid of fractions whenever I can. I don't care for fractions. There's our standard form. We got our A, our B, our C. Jump over the quadratic formula. Wouldn't necessarily need to write this every time because I would probably have my notes out, in which case I already have the quadratic formula written somewhere. If I have it written, I don't need to write it every single time. But I would definitely check to make sure I am plugging it in correctly, because there's a decent number of spots where you could mess it up a little bit. Particularly, the most common example that I see is people forget to include that square there. If you forget to include that, that'll give you a very different answer. No good. Okay, our B, we got 24. Our A, negative 4.9. But our C is still 0, since we started at position 0. All over 2A. Simplify it a bit. Since we've got a 0 here, this whole term goes away. Then we're just doing the square root of 24 squared, which is just 24, over 2 times negative 4.9 is negative 9.8. And then once again, solve that twice, once for it being positive, once for it being negative. So for negative, bar is a little too long. Here we go. That's better. Negative 24 plus 24 divided by negative 9.8. Negative 24 plus 24, 0. 0 divided by negative 9.8 is 0. And then negative 24 minus 24 divided by negative 9.8. That's a job for my calculator. So that's a total of positive 4 point. That would round up to 90 seconds. Just like last time, this is true. We were at 0 at 0 seconds, but this is what we care about. We're going to catch the ball .9 seconds after we throw it, based on how hard we threw it. We got a less time here since we didn't throw it quite as hard as that professional pitcher from example 1. All right, in the next video that should already be posted, we'll talk about solving a question like this, but instead of throwing a ball straight up into the air, it'll be a cannon shooting at an angle, so there's going to be quite a bit more to it. for now, that's a good spot to check. Make sure you understand what's going on here. If you don't, if you have questions, ask me questions about this before you move on to the next bit, because this is required for everything that comes next.